Welcome back, everyone. So today what we're going to do is continue our discussion on J2 that we had started last time. And then we're going to talk a little bit about drag, perturbation, and then wrap up this chapter. Okay, sounds like a plan. So last time we were about to derive the secular variation due to J2, and specifically I had said that we were going to do the work for Rayan specifically. So secular variation in Rayan. And if you remember, the trick is to do the integral over the true anomaly instead of doing the integral over time. So we're going to write the integral from 0 to 2 pi of d Rayan dt d theta. But to do that, we need to use the 1 over theta dot term in front of everything. Okay? So we're going to just recall that where our 1 over theta dot from last time was equal to r squared over square root of mu p, such that we can go back to our integral here and write 0, 2 pi of r squared over square root of mu times p. This is our 1 over theta dot term. This here, d Rayan dt, is just our Gauss variational equation that I gave you a couple of lectures ago. So I'm just going to copy it exactly as it is written in the lecture notes. All right, so those are derived for you. You don't have to rederive any Gauss variational equation every time you want to analyze the effect of perturbations on any orbital elements. You just grab the right equation from the notes and that's about it. So square root of p over mu times sine omega plus true anomaly. So that's our argument of latitude over sine inclination times 1 plus e cos true anomaly. Close the bracket and just report your d theta at the end, because this is the variable over which we're going to do the integral. All right. So how can we further simplify this? Well, we know that r squared can be written in terms of the orbit equation. So where r squared could be written as p squared over 1 plus e cos theta and square. So what we can do is substitute this for this expression in that equation here. And write secular variation in Rayan, which I'd like to remind you that this is the net variation in terms of radiance that Rayan will go through over one complete orbit. This is what this denotes. It's going to be equal to p squared over 1 plus e cos theta squared 1 over square root mu p times square root p mu, open the bracket, sine omega plus theta over sine I times 1 plus e cos theta, close the bracket, and d theta. So let's keep playing with this equation till we obtain something nice and that we can actually understand what's going on. Okay, well, I can cancel the square root p like this. I can multiply the square root mu together to get just mu. I can also combine the 1 plus e cos theta square with the 1 plus e cos theta. So let's do all of it in one go. So this is going to be p square sine argument of latitude over mu times sine inclination times 1 plus e cos, I'll forget the integral, cos theta cube d theta. All right. What are we going to do from there? Sorry. In the Gauss variation equation for Rayan, we have this times the trig functions here, but the numerator is actually combined or multiplied with fz, which is obviously the z component of your perturbation that you want to see the effect on Rayan. So what we're going to do next is keep that equation for now as it is. Okay, but then we're going to say that where our fz, we're going to pick fz due to J2, okay? And we had that from last time, which was, if you remember, minus 3 mu J2 mean equatorial radius of the Earth square over 2 R4 times sine of 2i times sine argument of latitude. Boom, like this. I'm not going to plug it directly into this expression because here I had replaced all my r's using the orbit equations. I'm going to do the exact same trick here. Because I have R4, I'll replace this with the orbit equation to the power 4 so that I'm able to cancel things out moving forward. I'm just going to say I have enough room to do it here. So minus 3 mu J2 radius of the Earth at the equator over 2 times P4. Right, I'm replacing my R4 with P4 over 1 plus E cos theta to the power 4. And all this multiplying sine 2i sine argument of latitude, like this. Okay, and now I am in a good position to substitute my fz into the secular variation in Rayan. But keep in mind that this derivation is only obviously applicable to J2, right? This is the J2 specific z component as seen in the orbital reference frame. If I ever ask you to do the same for drag, don't come to this equation and plug this result there as we're doing now, okay? Because this is very specific to drag. To J2, sorry. If you want to analyze the effect of another perturbation other than J2, then use the appropriate FR, F theta, Fz components, obviously, okay? So this back into that equation will give us integral 0 to 2 pi p square mu sine I sine argument of latitude over 1 plus E cos theta cube. Fz is all of this. So minus, I'm going to report here, 3 mu J2 mean equatorial radius of the Earth square over 2 P4 times 1 plus E cos theta to the power 4, and all this times sine 2I and sine, I'm just going to write, well no, let me write omega plus theta. Okay, everything is there, but my d theta like that. Oh, that is a big integral to evaluate. But don't worry, we know how to do it. Okay, let's cancel a few things. The p squared with the p4 cancel out to p squared on the denominator. I can cancel out the 1 plus e cos theta 4 over 1 plus e cos theta cubed. Like this. I have this term twice, the sine omega plus theta, sine omega plus theta. I'm going to say this is now square. J2 mu. Oh, the mu, I can cancel the mu here and here. And over here. 2p squared sine I on the bottom and 1 plus e sine I. Yeah, works out. So it means that this, I'm going to pull a few terms that won't affect the result of the integral outside the integral. So minus 3 J2 radius of the Earth at the equator square over 2p, where p is only function of semi-major axis and eccentricity, as you know by now. And because the integral won't get affected by this, I can pull it out. Integral 0 to pi of sine square omega plus theta times 1 plus e cos theta sine 2I over sine I d theta. Here we go. As simple as that, right? Okay, we're good. Next up, I'm going to use the fact that sine 2I could be written in terms of 2 sine I times cos I, and then simplify the sine I term here. So let's do this. Minus 3 J2 R Earth square over 2 p square, integral 0 to 2 pi, sine square argument of latitude, 1 plus e cos theta. And I can pull out my 2 in front of everything, the 2 for this trig identity, and just cancel the 2 on the bottom here. And here I'm going to get sine I divided by sine I, both get cancelled. So cos I, and then d theta. And actually the cos I can be taken out of the integral because this is not affected by true anomaly. Let me do it on another line. So minus 3 J2 R Earth square over P square. Cos inclination, integral from 0 to 2 pi of sine square omega plus theta times 1 plus E cos theta d theta, as simple as that. Wow. And now we need to evaluate this big integral. Well, we are lucky, my friends, because turns out that this from 0 to 2 pi is actually equal to pi, obviously, right? You all knew it. No, that wasn't obvious, but this is the result of that, okay? And in an exam, don't worry, you'll never have to solve such a complex integral by hand. That would just be too much. But this is the result we end up with for the secular variation in Rayan due to the J2 perturbation, okay? Now with this, we can go one step further and look at the average rate of change in Rayan due to J2. So I'm going to write the average rate of change in Rayan due to J2 will be equal to this quantity over one orbital period, where one orbital period is 2 pi over n. So this divided by 2 pi times n. Or in other words, minus 3 J2 R Earth square over P2 Where did the pi term go? Did I have a pi in there? Oh boy. Oh yeah. This in red. Yeah, okay. Sorry about that. Cos I thought it was done, but I wasn't done. Cos I times pi divided by 2 pi times n. So the pi terms cancel out. I'm going to be left with minus 3 J2 R Earth square over 2 P square n and cos of the inclination. Here we go. Average rate of change in Rayan due to J2. Okay? This is one of the effects caused by J2. If you were to do a similar process for all the other orbital elements, and don't worry, we're not going to do it together, you would realize that average rate of change in semi-major axis will be equal to average rate of change in eccentricity equal to average rate of change in inclination, and all of these three equal to 0. So in other words, the J2 perturbation does not affect our semi-major axis, eccentricity, and inclination in any way, shape, or form. But we would get a non-zero average rate of change in argument of perigee here, and this one will be equal to minus 3 J2 our Earth square over 2p square times n. So it looks a bit like this one, but then here we would have 5 sine square of inclination over 2 minus 2. Okay, so all in all, J2, as you can see, only has an effect on Rayan and on argument of perigee, which, believe it or not, can be a good thing for us. And actually, through the careful design of orbital elements, we are able to take advantage of those to design 2 types of very specific orbits. The first one is designed by looking at this effect, and that's going to give us what's known as a Sun-Synchronous Orbit. Okay? So if you think about it, and if you look at the Sun-Earth spacecraft system, this is Mr. Sunshine, happy as always. And say you look at the Earth, throughout a year at 4 different positions. And if you look at what's known the terminator line, which is the line that divides the Earth in terms of sunlight or shadow, right? You have this in the shadow, this part in the shadow here, this is in the shadow, and here the top part of the Earth will be in the shadow. Okay, this is a day and night cycle as seen at 4 different positions throughout the complete year of the Earth's path around the Sun. Like this, okay? So if there was no J2 perturbation affecting the orbit at all, which is not possible because J2 is there no matter what you do, and you were to look at your orbit in a top-down view, okay, so this is a top-down view of the system, you could get an orbit that looks like this, for example, okay? And that orbit would be inertially constant in time throughout the year because there's no J2 perturbation that would go and modify the right ascension and ascending node such that the orbit would always look the same seen from the inertial perspective like this. Okay? Which means that the time at which the spacecraft would cross the equator, the local time, which is known as local time of ascending node. So let me go back here and draw a quick orbit in 3D to complement this top-down view. You have the Earth, you have an orbit. You don't see that? No. And the equator of the Earth. This is where the orbit crosses the equator from south to north. So then we call this direction of the ascending node, which is our n vector. And say the star of interest Aries in the direction of the vernal equinox is somewhere over here. Then we have our IX unit vector of ECI, and therefore our right ascension of ascending node happens to be this angle. Okay? So the local time of ascending node is the time on the ground whenever the spacecraft passes directly over the equator. Okay? So because the Earth rotates underneath the orbit, then that local time of ascending node keeps shifting, because the local time at that particular point along the equator when the spacecraft goes from south to north could be noon, and then an orbit later could be 2 p.m., and then 4 p.m., 6 p.m., then boom, you're in the shadow, and then sunlight comes, and then 2 a.m., 4 a.m., 6 a.m., and so on and so on, okay? Which means that without J2, this is what we would see. All right, local time of ascending node would keep shifting, as seen here, okay? Because if this is the noon direction, right? Noon, and noon, we see that here the spacecraft could be crossing the equator, say, this is noon, maybe 3 p.m. Here, maybe this is noon, midnight, maybe 9 p.m. or something like that, that point. Here would have something like 9 a.m. maybe. And here, I don't know, but you see that would keep changing, okay? So it wouldn't always be the same thing. But if you happen to design the orbit such that the average rate of change in Ryan happens to be 2 pi over 1 full year, that's 364 point something, we should say 365 days for the sake of this discussion. If you happen to be able to design the orbit such that you get this particular value for the average rate of change in Ryan, that would mean that you would always keep the same local time of ascending node throughout the orbit. Instead of having a fixed orbit inertially, which would mean that the local time of ascending node would keep changing, then what you would get is an orbit that shifts at a rate. So the orbital plane would rotate about the spin axis of the Earth and complete 1 full revolution in 1 year, such that if you just zoom on one section of the Sun-Earth system, this is your shadow of the Earth. By the way, this line that divides the shadow and the sunlight is known as your terminator line. Terminator. And that always here is your noon direction. So here, if this is noon, that could be this point here, 3 p.m. again. But if you want to maintain a 3 p.m. local time of ascending node through the careful selection of the orbital elements with which you can calculate that and end up with a specific value, means that instead of having 3 p.m. here and keeping the same orbit and boom, ending up at noon here, then the orbit would shift such that you always maintain a 3 p.m. local time of ascending node. Okay? So this is a sun-synchronous orbit. In other words, the orbit shifts throughout one complete year at the same rate that the Earth rotates above the sun, such that the illumination conditions are always constant for that particular orbit. And this has a lot of benefits for Earth observation satellites, for example, that want to image something, right? Having always the same illumination conditions for your sensor has obviously some great benefits. A couple of useful orbits of sun-synchronous family is the dawn-dusk orbit. I'll draw it in red. A dawn-dusk orbit is essentially an orbit that rides along the terminator line, okay, and shifts throughout the year to always follow the division between daylight and nighttime, okay? The main benefit of a dawn-dusk orbit like this, which is 6 a.m. local time of ascending node and 6 p.m. local time of descending node, is that for power generation's perspective, the spacecraft is always seeing the sunlight, right? It's never in the shadow casted by the Earth. So from a power perspective, the spacecraft goes around here along this line, and therefore its solar panels are always receiving the sun's energy for recharging the battery. So that has a lot of benefits, okay? I'm going to say power happy. And then you have other types of common sun-synchronous orbits like the 3 a.m., 3 p.m., which is this. There's the noon, midnight orbit. I can draw in green. So this is midnight, this is noon. So the spacecraft orbits around the Earth and the orbital plane shifts throughout the year to always maintain that orientation with respect to the sun, and so on and so on. Okay, so noon, midnight is also a common sun-synchronous orbit. So how can we design the orbit to end up with this particular value? Well, it's easy. You just go back to the equation I gave you for the average rate of change in Rayan due to J2, and for a given orbit size and shape, that is for a given semi-major axis and eccentricity, you will realize that the other parameter you can play with is your inclination, right? Because we have this equal to, where's that equation? Here. We had minus 3 J2R Earth square over 2P square N cos I. Those things are just constant. This is function of semi-major axis and eccentricity. This is function of semi-major axis. So the only other parameter you have control over as an orbit designer is the inclination, okay? So by inclining the orbit properly, you will create a rotation of the orbital plane, and you do the math such that you end up on this side, and you have to convert the days in seconds, obviously, to this particular value given the orbital shape and size. You could solve that equation for I, the inclination, that would give you this, okay? By the way, this here, the average rate of change in radian, is also known as the nodal regression rate, just so you know. Okay, so sun-synchronous orbits are orbits that are inclined such that we end up with the nodal regression rate exactly equal to this value, such that the orbit shifts at this rate to always maintain the same orientation with respect to the sun, and therefore maintaining a constant local time of ascending node, and in other words, always have the same illumination conditions. Okay, so sun-synchronous orbits are very popular for Earth observation satellites. But also, if you look at the average rate of change and argument of perigee, that was the other effect of the J2 perturbation, which was non-zero. You could also make use of it to design what's known as a critically inclined orbit. Okay, so critically inclined orbit. So essentially, a critically inclined orbit is an orbit for which the average rate of change in argument of perigee turns out to be zero. Okay, such that the perigee is not spinning in the orbital plane. Or if you will, the perigee will always be over the same kind of latitude of the Earth. So otherwise, what you would end up with is an orbit with, say, the perigee. If you look at a highly elliptical orbit, the perigee could be here, and then the average rate of change in argument of perigee to be equal to a non-zero value would mean that this vector, eccentricity vector that points at the perigee, would spin. So at some other time in the future, it would have spin up to here, for example, such that now the orbit would look like something like this. And at some other time, perigee would end up being on top here, and so on and so on. Right, so the perigee here, 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 and so on and so on. So you see a great kind of motion of the orbit as time goes by. So that could be useful, but typically this is not very useful. And in fact, Russians back in the Cold War era had made use of the fact that we can actually go back to this equation and figure out orbital elements such that the inclination, which is part of this calculation, and give us a net average rate of change in argument of perigee to be equal to zero, such that the spacecraft would spend the longest amount of time of its orbit over the United States. Was that over the United States? No, over, I think they wanted to have the perigee always close to Russia. That's what they wanted, okay? So this is the Earth, and say Russia latitude would be here, so perigee could be here. And they were using a highly elliptical orbit, such that the spacecraft would spend the greatest amount of time here, and then would just swing back real quick over Russia to transmit data that they would have gathered as a spying satellite, spying on other countries, and then accelerate, transmit the data back to Russia, fly back down, and then spy on other countries, get data, transmit data back to Russia, and so on and so on. And the way that they've been able to achieve it was to make sure that the perigee would always remain in the same spot and not end up perigee over here, and then spending a lot of time over Russia, which they weren't interested into doing. Right? They were not interested in spying themselves. They wanted to spy other countries during the Cold War. So if you look at the equation for the average rate of change in argument of perigee due to J2, you would figure out that the two inclinations that would give you this equal to 0 are equal 63.4 degrees or 116.6 degrees. All right? So that concludes the effects of J2 on low Earth orbit. So in order to come down to these practical implications, we've gone through the entire process of analyzing the J2 perturbation, starting from the geopotential function, getting the perturbing acceleration vector, expressing it then in terms of its components in the orbital reference frame, then extracting out of it Fr, F theta, Fz, plugging this back into the Gauss variational equation, using the Gauss variational equation, dividing this with theta dot, and doing the integral from 0 to 2 pi over the true anomaly variable. And then we took that divided by the orbital period to get the average rate of change in Rayan and the average rate of change in argument of perigee due to J2, okay? This discussion we've had so far today is limited to J2 perturbation. If I were to give you a random perturbation in an exam, don't use the formula as we've just used for J2 specific, yet the process is the same. Always go back to expressing the vectorial equation of your perturbing acceleration, which could be whatever, inside the orbital reference frame, extract Fr, F theta, and Fz out of it, and just follow the process. Okay? So again, this concludes the discussion on J2. Now what I want to do next is look at drag. So drag perturbation. And the reason why I want to do it is because drag is the dominant perturbing acceleration in low Earth orbit that is not caused by a gravitational source. So drag has a tremendous effect on spacecraft that are orbiting close to the Earth, or low Earth orbits, if you will. So that would be in 3.2.2. We're going to look at atmospheric drag on the orbit of spacecraft. So if you look at the perturbing acceleration due to drag, like this, we can model it as -1/2 times the drag coefficient of a spacecraft, which is typically a box-shaped object. So CD times the frontal area, which is facing the flow or facing the atmosphere, over the mass of the spacecraft, the atmospheric density of the Earth. And because this is a vector equation, you need a vector somewhere, yet those are all scalars. So the vector part comes from the relative velocity vector between the spacecraft and the atmosphere, okay? Drag coefficient for a spacecraft between 2.2 to 2.5 is a good approximation of a cubic shaped object on orbit. Mass of the spacecraft is whatever. The frontal area, you could either model it as being by taking the dot product of the normal vector for each face comprising the spacecraft with the velocity vector to then only compute the ones that are facing the flow, or you just pretend that the spacecraft is always oriented with one face only being exposed to the atmospheric drag effect. So either constant or time varying. If you want, again, to consider time varying frontal area, you need to model the orientation of the spacecraft, so its rotational motion. So in this course, we will only focus on constant frontal area of the spacecraft. Rho is the atmospheric density, which decreases exponentially with altitude. And VR is the relative velocity between the spacecraft and the atmosphere. So in terms of mathematical relationship, we can model this last term as being the velocity vector of the spacecraft times the angular rotation of the Earth about its spin axis. That's your 2 pi per day, more or less, cross product with the current position vector. So here, by modeling it this way, we assume that the atmosphere in which the spacecraft is evolving is actually stitched to the Earth. So as the Earth rotates, it swings its atmosphere with it at the same rate, okay? So that's why we can use this kind of simplistic model for the relative velocity between the spacecraft and the atmosphere. Okay, next one up to look at is how can we model the atmospheric density at a given altitude? Well, there are many, many models out there that we can use, from very simple ones to highly accurate ones. So perhaps one of the most simplest model is the exponential model, which goes like this. H, where we're going to define each parameter in that equation. So rho naught is the base density. Or, well, base or reference density, same thing. Which is a constant for a range of altitudes you're operating in. H naught is the reference altitude, which is a constant for a range of altitudes. So say, you know, your spacecraft will operate in a range of 500 to 700 kilometers. There are actually a bunch of tables in astrodynamics textbooks that are listing a bunch of base density or reference density and reference altitude for a specific range of altitudes. So between 500 and 700, we get one number here and another number here that can then plug into this expression. Z is your actual geodetic, not geocentric. Remember our discussion we had in the past? So actual geodetic altitude. So that is the altitude above the surface of the Earth. So that is the Earth and that is the orbit. It is not from the center of the Earth, but simply this dimension from the very surface to the orbit, which can vary if you have an elliptical orbit, or which could be constant if you have a circular orbit around the Earth. Okay? This is Z, and this is Z, which you get by just taking the norm of your position vector minus 6,378. Yeah, that is the radius of the Earth, okay? And capital H is your scale height. Which is another constant for a range of altitudes. So essentially everything is constant in that equation, but the current altitude, which vary with time. And this is how you can figure out the density in which the spacecraft is currently traveling in. And obviously, because of this formulation, you could see that it decreases exponentially with altitude. So here, you would experience quite a bit more drag than you would at this other point here near the apogee. And in fact, near the apogee, it's as if there was no drag at all. But for the purpose of the follow-up development, we're going to use this simplistic drag formulation, but we're going to go one step further in simplifying it and just assume that we're going to use directly the spacecraft velocity instead of the relative velocity with respect to the atmosphere, just to simplify the development a little bit. Yet the practical implication at the end that we will discover will be exactly the same, regardless of which model we use, okay? Okay. So let's analyze the effect of drag on orbital elements now. And we're going to do the work for the semi-major axis only due to time constraint. But anyway, this is the greatest impact, okay? So drag has a big influence on the semi-major axis, and we're going to see how to quantify it. So to do the work, we're not going to use the same procedure as before, i.e. taking the Gauss original equation and so on and so on. This is kind of an ad hoc methodology, yet it is very quick to analyze the effect of this particular perturbation. But just keep in mind that this is very specific to drag, and specifically the effect of drag on semi-major axis. Don't try to generalize the following development to any perturbation on any orbital elements. That would just not work at all, okay? So to do the work here, we're going to begin by taking the derivative of the specific orbital energy, the EDT, and specifically using the expression for energy that we had, which was the minus mu over 2a, such that the derivative would give us a dot mu over 2a squared. Okay? So this is all for the EDT, but that's not what we want. We'd like something on the left-hand side that looks like a dot, the time derivative of semi-major axis, which is analogous to the Gauss original equation for semi-major axis, yet using a different thought process here, okay? We're going to say, based on that equation, if we replace this with E dot, we're going to have E dot times 2a squared over mu. This is the rate of change in semi-major axis. What is E dot? Well, E dot, time derivative of energy, yet we're not going to calculate it using the same expression. That would just be leading us nowhere. So instead we're going to do the time derivative of the other expression we have for the specific orbital energy, which is specific kinetic energy minus mu over r. But here, instead of writing the speed square, we're going to write it slightly differently, and specifically we're going to write velocity dot product with itself, okay? Because we need to arrive at a point where we have v dot in the expression such that we can use a two-body equation plus the drag perturbing acceleration and see the effects on our semi-major axis, okay? Just a little trick here that we're going to use. So let's apply the time derivative to both of these terms. So here we get chain rule, velocity dot product velocity over 2 plus velocity dot product velocity inertial derivative over 2. And then here would become plus r dot mu over r squared. This is for E dot. And then within E dot, we have this term here. And actually, let me just simplify it a bit further by combining these two together and remembering that the dot product is commutative. And then just write v dot product v plus r, and this mu over r squared. Now, looking at the speed here from chapter 2, I believe, or even chapter 1, I'm not too sure, we had derived this expression for r dot, which was position vector dot product with velocity vector over distance r. Okay? Then just report that equation here and keep it on the corner. E dot 2a squared over mu. Okay, now I am at a point where I have E dot equal acceleration dot product velocity plus this, which is r dot product v over distance, but here was also over distance squared, so that becomes distance cubed times mu. Okay. Now, what else do we know in this equation? Do we know an expression for v dot or the acceleration? Yes, we do. And that would be the two-body equation plus the perturbing acceleration we are considering here, which is drag only. So we're going to say where v dot is equivalent to a, which is equivalent to r double dot, which is what we're familiar with, equal minus mu times r vector over distance cubed plus our perturbing acceleration term due to drag, which, considering the most simplistic model ever, will be minus 1/2 CD frontal area over mass density, and just the velocity of the spacecraft itself, not the and not the relative velocity. That's what I was after. Okay. So minus this, minus 1/2. Okay, that works out. So let's plug this back into here and see what we obtain. So minus mu r vector r cubed minus 1/2 CdA over m rho v scalar v vector, all this dot product with v plus r dot product v over r cubed times mu. So all this is just for the rate of change in orbital energy. So you are, yeah, that works out. So here, look at what we have. We have minus mu r vector over r cubed dot product v plus r vector dot product v over r cubed times mu. So these two terms actually cancel out, okay? And we are left with just minus 1/2 CD A m rho v v square, all this dot product with itself plus nothing else. Okay? And you know by now that a dot product of a vector with itself is just its norm square. So I'm going to write that it is minus 1/2 CdA over m rho v squared times v gives us v cubed simply. And all this is for E dot, but yet that's not what I was looking for. What I was really looking for is the rate of change in semi-major axis due to drag. And now we have the rate of change in orbital energy due to drag, right? This is all coming from drag. If there was no drag being experienced on the spacecraft, all this term will go to 0, and the rate of change in semi-major axis will go to 0 too. But because of drag, those things aren't 0 anymore, so that we can come back and write dA dt equal to minus 1/2 CdA over m plus for density speed cube times 2 semi-major axis square over mu. Let's put it there. Okay? And the twos cancel out, and I'm going to be left with dA dt equal minus CD times A times rho times speed cube times A squared, all this over mu times m. Boom. And this is how the semi-major axis varies when a spacecraft is experiencing drag on low Earth orbit. So what we see is that I'm thirsty. I'm going to drink some green tea again. Which isn't hot anymore. It's very cold by now. Yet it's not that bad. So what do we see? Well, we see that the semi-major axis, its rate of change, will be negative, right? Because all the numbers here are actually positive numbers. Yet we have the minus sign. So that makes a lot of sense, right? Because drag removes energy from the spacecraft. And I told you that already a couple of times. So imagine if drag, instead of decreasing the semi-major axis, would increase it. Wouldn't that be crazy? You would get free energy on orbit. So the spacecraft would keep gaining and gaining and gaining energy and getting to higher and higher orbits and becoming happier and happier. I mean, that's just nonsense. That doesn't work like that. So in practice, what happens is that, say you have the Earth, and you have a highly elliptical orbit, meaning that the distance between the perigee and the apogee are very large. So here, say you have the perigee and the apogee here. Yeah, through my equations, of course. dA dt. Something like that. No, not good enough. Let's bring the Earth down a little bit. Oh boy. It is getting late and my drawing skills are going through the drain. Okay? Can you all see that? This is the Earth. This is a highly elliptical orbit with a very high apogee and a very low perigee. So what happens in practice is that as a spacecraft complete multiple orbits around the Earth, and whenever it reaches this region here, or the altitude is quite low, with respect to the ground, it means that the drag being experienced is going to be significantly higher than anywhere else along the orbit. Okay? In other words, the atmospheric density in this region is significantly higher than over here, because, say, the region of relatively high atmospheric density would be through this kind of altitude range here. Will mean that here the spacecraft does not experience drag, no drag, no drag. Oh, a little bit of drag. Oh boy, a lot of drag, slows me down quite a bit. And here again, I can breathe. Okay, no more drag, no drag at all. Here is a walk in the park. It's really easy. I'm not decreasing. I'm not losing any orbital energy. So the spacecraft would only lose orbital energy due to drag near the perigee, say in this section. And as a result, it's almost as if the spacecraft in this region would fire its thrusters backward to slow itself down. So come here, slows itself down, meaning that this is not where the spacecraft would see a net decrease in altitude, but that would be here. Because now you have quite a bit less energy to swing yourself around the Earth. Come back here again. Oh no, a lot of drag. Oh, I can barely go through here, but yet I have less residual energy to complete the orbit. So what's going to happen is that slowly the spacecraft would then lose energy and spiral down through the atmosphere and eventually burn down in the atmosphere. And as you could see through the process, I went from a highly elliptical orbit and slowly decreasing the apogee altitude, yet not changing much the perigee altitude. So the result is that I am effectively decreasing the eccentricity of the orbit by completing one orbit after the other. Okay? So in other words, I am circularizing the orbit. I went from a highly elliptical orbit down to a circular orbit that spirals itself down into the atmosphere. This is the effect of drag. And all this because we have the minus sign here. Otherwise, that would have been positive. We could have started with the circular orbit, and then instead of spiraling down through the Earth's atmosphere, we would just increase our altitude like that without firing any thrusters and eventually escaping the gravitational field of the Earth. Wow, that'd be cool. But just because of this little minus sign, this is not how it works. So this concludes Chapter 3, our discussion on orbital perturbations. Hopefully now you understood the necessity to have the tools we have now at our disposal, which is the Gauss variational equations, and how to use them practically. And again, it may sound like a broken record, but the first step, if I were to give you some random perturbation in terms of vectorial equation, is really to express that in terms of its components in the orbital reference frame, and then extracting out of it the FR, F theta, Fz components, plug this back right away into the Gauss equations, which are provided for you in the lecture notes, and we did the derivation together. And once you have that, feel free to look at the secular variation or the average rate of change and draw your own conclusions based on that, okay? And specifically here, we did some more detailed work on the effects of J2, creating a time variation of our Rayan and a time variation in our argument of perigee. And we saw that these two could lead to two beneficial effects in terms of creating Sun-Synchronous orbits, for which their L tan, the local time of ascending node, remains constant because the orbit shifts at the same rate that the Earth rotates about the Sun, and also a critically inclined orbit to ensure that the perigee does not shift inside the orbital plane by selecting the inclination properly to null out the average rate of change in argument of perigee. And finally, we looked at drag and specifically its effect on the semi-major axis and how it leads to a decrease in orbital energy, circularization of the orbit, and eventually atmospheric burn down. Okay? Thank you so much for following these lectures. Hope you enjoy the process. Hope you learned something new today again. And as usual, see you next time.